Okay, we're going to go through the third part of this January 22 paper, Unit 5, Physics, Edexcel International A-Level. So topics covered are thermodynamics, radiation, oscillations, and cosmology. So in the first two videos we did part 1, the multiple choice, part 2, questions 11 to 16 of section B. Now we're going to do the last 4 questions of section B, 17 to 20. I just want to show you that we finished off with question 16. The second part of question 16 is shown on the screen now. My answers are there for you to have a look at. It's about the difference. I just want to show you the mark scheme for this question. So if you want to slow it down, because I'm not sure I have explained this part, 16a, as clearly as possible, and here they've got an alternative way of answering the question, so I thought it might be useful for you to analyze your own answers according to the mark scheme. Okay, I think even the mark scheme could be clearer, but those are what they give the 3 marks for in 16a. Okay, so the next question is question 17, and it's about a loudspeaker which uses low frequency sounds and high frequency sounds. It explains what a loudspeaker is made of. So it says a music system has a number of loudspeakers. One loudspeaker produces the low frequency sounds. They're called woofers in the trade because they woof like low frequency. This loudspeaker consists of a coil connected to a cone. So here you have the cone, yeah, and here you've got the coil. So this is the coil where the current is going in a circular direction around the magnetic one of the poles. So you might have, for example, this side could be a north, this could be a south, and vice versa, whatever. As long as you've got a magnetic field and the coil is in it, you've got both sides. So I'm not exactly sure of the mechanism by which they do the magnetic field, but there is a magnetic field, permanent magnet. Okay, so the magnet's on the outside, the coil is inside, and the oscillations are going in and out. And it's oscillating because the current is alternating. So the direction of the current keeps changing. The coil is in the region of the magnetic field. So the magnetic field is between the poles here and between the poles there. Okay, so there's a uniform field between the poles. And so when the coil is either going to be pushed up, depending on the current direction, or pulled back, depending on the current direction. Okay? So that's how a loudspeaker works. You did this also in GCSE. The question wants you to explain how an alternating current, AC, in the coil causes the cone to oscillate with the frequency of the alternating current. So how do you verbalize your answer? So I've put the current in the coil, yeah, has a magnetic field of the current. So there's a magnetic field around the current anyway, its own magnetic field. It interacts with the field of the permanent magnet, which is surrounding it. Okay, so there's 2 magnetic fields in effect. This produces a force which is at right angles to the field. So the field is this way, and the force is at right angles either up or down. So the coil moves in and out. See arrows drawn. So I've referred to my diagram. So that's a good idea to show that you're using the diagram as a way of helping your words get your clarity of thinking across. Okay? So because they're marking you on your ability to communicate clearly. So the coil moves in and out depending on the direction of the force, which changes when the current, AC, changes direction. Okay? So I think that's how you would get the 3 marks. Each of these points is worth a mark. Okay? There are variations on that theme. So that's question 17, first part. Part B then, it says a signal of constant frequency is applied to the loudspeaker. So why is the loudspeaker question in Unit 5? Because obviously a loudspeaker is an electromagnetic device. Well, the answer is because the coil moves with simple harmonic motion. So it's also a simple harmonic motion analysis. And the loudspeaker emits a sound of frequency 75 Hertz. So here also we're talking about sound, which is from Unit 2. When the loudspeaker is producing this sound, 75 hertz, the coil moves through a maximum distance of 3.5 millimeters. Maximum distance means from bottom to top of its oscillation. Okay, that means the amplitude is half that, because the amplitude is measured from the center of the oscillation. So don't get confused. They're trying to confuse you. The maximum distance traveled is 3.5. That means from the top of the peak of the movement to the trough of the movement, if you like. So the amplitude is 1.75 millimeters, which you've got to convert standard form 10 to the minus 3 meters. Calculate the maximum velocity of the coil. Well, this equation is given to you on the formula sheet, okay? And there's a negative sign there just to show that it is a decreasing velocity as sine omega t decreases, so it changes. So we'll get to that in a moment. But the maximum velocity is when sine omega t is a maximum, okay? Because obviously sine omega t varies between 0 and 1. So the maximum velocity will be when this is 1. Therefore, the maximum size or magnitude of the velocity will be a omega, okay? The negative indicates the direction is opposite to displacement, okay? Now, so when you displace it one way, the velocity is the other way, okay? Anyway, you don't really need to worry about the negative sign. Therefore, the other thing you need to know is that omega, so a omega will be the maximum velocity, okay? And omega is 2 pi f, also on your formula sheet, okay? So if you know the a is half the maximum distance moved between top and bottom, so you put in your value 1.75 times 10 to the minus 3 meters, multiply by 2 pi times the frequency which is given to you, you will get the maximum velocity, which should give you a negative answer, but the minus isn't important because we only care about the size of the velocity, and that comes to approximately 0.82 to 2 significant figures. Why 2 significant figures? Because they've given you 2 significant figures here and 2 significant figures there. So that's all the accuracy that we're certain of. Okay. The next bit. State the position of the coil when the velocity is at the maximum. Well, obviously it's at the end when the the displacement is at its maximum, the velocity will be 0. So at each extreme it turns around, so the velocity must be 0. So it's in between. The velocity will be a maximum as it travels through the center of the oscillation. Okay, it then slows down because it's decelerating, and then it will get to 0 and then return back through the equilibrium position at maximum velocity again. So that's just knowing that, okay? In the question before, you can probably work out, you'll get 1 for the answer, 1 for the calculation, and 1 for knowing which equation to use. Something like that, okay? Or it could be that you get a mark for the a equals 2 pi f. Yes, so you'll get a mark for knowing that you've got to convert it. So 1 for putting the numbers in correctly, 1 for doing that. Yeah, so putting this is 1 mark, using the correct numbers, and so on. And then it says, at a particular frequency, the loudspeaker cone starts to oscillate with a very large amplitude. Why? Explain why this effect is observed. Well, it's resonance. In one word, it's resonance, but you want 2 marks. So I've given you 3 ways of getting 2 marks. When the frequency oscillating the cone, I'm misreading my own word. The cone matches the natural frequency of the cone. And remember, every physical object has its own natural frequency. Okay, so when it happens that the 75 hertz, say, or whatever, the frequency that the loudspeaker is producing, the AC is producing, when it happens to match the natural frequency of the cone, based on its dimensions, etc., it will have a natural frequency. This is when resonance occurs, which is when there is a maximum transfer of energy from the vibrating coil to the cone. So the amplitude builds up. At this point, when you get resonance, amplitude builds up, okay? It's like if you're pushing a child on a swing. If you time your oscillations, your pushes on the child on the swing, at the exact moment when it's at the end of the swing, you will build up the amplitude that way, because then the forcing frequency, you're pushing the child each time you put a force on. If it's synchronized with the natural frequency of the swing, you will build up amplitude, and that's maximum energy transfer. Okay, question 18 is about Kepler. Kepler, in 17th century, Kepler proposed his law of harmonics, okay, law of harmonies for planetary motion. This law suggested that the ratio of the square of the orbital speed, t, square of t, to the ratio to the cube of the mean radius, r cubed, has the same value. In other words, t squared is proportional to r cubed with k in it. Okay, so or you could say what he's saying: t squared, ratio of t squared to r cubed, yeah, has the same value. That means it's a constant. Mathematically, the law of harmonies can be written this way, or it can be written this way. Okay, both are correct. They are the same, where k is the constant. So the table shows the data for Earth and for the Moon. So the period for the Earth and the period for the Mars, and then the radius for the Earth and Mars. Obviously Mars is further away. So show that for both Earth and for Mars, k in both cases has a value of about 3 times 10 to the minus 19 units, will be a second squared divided by meters cubed. Okay, now there's a typo here, they've got times twice. Okay, so just, I don't know if they put a note for this when the exam, I noticed the second time round. So because I'm writing the k here, so I'm going to divide t squared for r cubed for both Mars and for Earth. Okay, so for Earth, you take the value for t, square it, you take the radius for the Earth, cube it, divide the square by the cube, and you'll come up with 2.959 times 10 to the minus 19 units, second squared meters to the minus 3. You do exactly the same for Mars, and you come up with 2.967 times 10 to the minus 19. Well, you can see they're very close. So you have to go to the third decimal place to see a variation. So both k for the Earth value and the k constant value for Mars, both of them to two significant figures, are exactly the same, 3.0, which is what they want us to do. Okay, so both values are the same, okay, which is answering the question. So that's the first part of question 18. The second part is Kepler's law of harmonies was derived later by Newton. Newton applied his law of gravitation to a planet moving in a circular orbit around the sun. Okay, now remember that no planet is has a perfect circular orbit, because all objects are moving around the center of mass of the whole system, and the solar system obviously is dominated by the sun, so it's roughly the center of the solar system, but it will wobble a little bit, so even the sun is moving around the center of mass of the whole solar system. That's why you never get perfect circular motion, but to an approximation. If we use this theory that there is circular motion, determine a value for k by applying Newton's law of gravitation, which is F equals gmm over r squared. There's Newton's law of gravitation, yeah, to a planet m moving in a circular orbit. Well, circular motion means there must be a centripetal force, and centripetal force, circular motion, is mv squared over r. The m is common, so you can get rid of them. So you can equate the centripetal force is due to Newton's law of gravitation. So you can equate the Newton's law of gravity, Newton's law of gravitation force, with this force towards the center of the circle, which is mv squared over r, where v equals 2 pi r over t, okay? Circumference of the circle that you're traveling around in the period of orbit. So if you put the value, so m's have cancelled out. If you put the value of v squared using this equation, it will be 2 pi r over t all squared. And this side, the r's cancel. One of the r's cancel from this side, and this r goes. So you can cancel the r's. So all you're left with is gm over r on this side. And then you can square this brackets out. There's nothing on the denominator now. So 2 pi r squared is 4 pi squared r squared. And the bottom becomes t squared. Okay, then all you need to do is to rearrange and simplify it. So t squared will be equal to 4 pi squared r cubed over gm. So if you can do that manipulation algebraically, you will see that the constant of proportionality that we had from the first page, so you see this equation and this equation, t squared on the left hand side, t squared on the left hand side, r cubed, I've used little r, I should have used big R again, r cubed on the right hand side, then the constant here must be equal to this value. That's the constant. Okay, so what have we done? Determine a value by k using this Newton's law of gravitation and circular motion. So you're combining Newton's law of gravitation and circular motion to derive Kepler's laws and to come up with another way of working out k. So it'll be 4 pi squared, which is just a number, divided by g, divided by m, where m is the mass of the sun, and the mass of the sun is given to us here. So if you do that, you come up with the k value is 2.97 times 10 to the minus 19. So if you noticed before, 2.97 there, that's exactly the same as what we got for Mars, 2.967, and for the Earth, 2.96, if you like. So another way of confirming the value is that should be written in here, ideally. Okay, so that's part B. Now it goes to part C. So let's just read it first. Jupiter is the most massive planet in the solar system and has many moons. So Kepler's law of harmonies applies to the orbiting moons. Now, however, so this time we're talking about the Jupiter system rather than the solar system. However, the value of k for the moons is not the same as the value that applies to planets orbiting the sun. So this is a however, so it doesn't tell us why it's not the same, because not following it. So let's see. So because it's a different system, I suppose, because the values are different, the central mass in this case is going to be Jupiter. Okay, so gm, if you like, the values that you're using will give you a different constant. Okay, you don't need to know why. So this is just extra information. Then it says Ganymede is Jupiter's largest moon, and then it's giving data about Ganymede. Its orbital radius is this much, so that's the R of Ganymede, and orbital has an orbital period of 172 hours. Okay, so this is the period of Ganymede, that's a capital G. Another moon, Io, has an orbital radius of 4.22 times 10 to the 8. So this time it's R of Io, so I've written I and O. So we have the two radius, the radius for Ganymede, and the orbital radius for Io. Okay, so we have three values. Okay, two radii and one period. Okay. They want you to calculate the missing period of Io about Jupiter. So we know again, t squared over r cubed is going to give us a constant. So this time we know that if we do it for Ganymede, t squared of Ganymede divided by r cubed for Ganymede should equal the t squared for Io, they've put it as 1, so I've left it there, divided by the r cubed, for Io, which is here. So if you do that, the only unknown, so we know this, and we know this, the only unknown is that. So make this the subject of the formula. This is a derived formula then. Yeah, so again, algebra. Oh dear, it's just off the page, I apologize. So all I've done is I've done it twice. So I've put the Ganymede values in the t squared over r cubed. I've put the Io values. The only one we don't know is the period for Io, which has been labeled T1. Okay, so if we do that, this is the rearranged equation where we want to work out the missing Ti. So basically this goes on the other side. Okay, so if you follow the algebra, you then put the numbers in. You can leave it in hours. Okay, because it just wants the orbital period, and you do the necessary mathematics, T1 will be the square root of this side when you multiply it all out, and it comes to 42.6 hours, or that's 3 significant figures, and if you want 2 significant figures, it'll be 43 hours. Okay, so it's up to you if you do it to 2 or 3 significant figures, I would say, because you have 3 significant figures, 3 significant figures, and 3 significant figures there. Okay, that's the end of question 18. Question 19. Okay, the end of the paper often finishes with astronomy. The astronomer Hertzsprung used parallax to determine the distance to some of the variable stars known as Cepheids. Okay, I don't know how you pronounce that. I call it Cepheids. Okay, using parallax measurements, astronomers can determine distances to all stars, any star, with a parallax angle larger than 2.4 times 10 to the minus 7 radians. In other words, if you look at the distant star, so say here's a star that you're looking at. So there's your star. If you look at it from one side of the sun, when the Earth is, say that's March 21st, equinox, you're looking at it, it produces an angle where this is a distance between the center of the sun and the center of the Earth, which is known. Then you can work out the angle. So if you can measure that angle, yeah, and then you do it again 6 months later, it'll be the other side. It'll be double that angle. So if you can work out the angle from the Earth, Sun, you have a right angle triangle there, you can do some trigonometry. But for very small angles, you actually don't need sine, because the ratio of these numbers, because it's such a small angle, will actually be the same whether it's you put the sine to the minus 1 in there or you just use the values. Okay, so either method will work. So we got to do what it's asking. The variable star, it says Alpha Centauri, so this would be Alpha C, Alpha Cephei, is 4.6 times 10 to the minus 17 meters. So that's 4.6 times 10 to the 17 meters from Earth. So this is Earth. That's meant to say E. So that's Earth at this angle. So actually Earth will be there and the sun will be here. Okay, so deduce whether the distance to Alpha Cephei could be determined from the parallax method. Remember, it can parallax measurements. It can only be done if the angle here is greater than 2.4 times 10 to the minus 7 radians, okay, which is a very small angle. Because obviously when the angle gets too small, we can't measure it. So that's why there's a limit to this method. So we've got to deduce whether the angle is basically larger than 2.4 times 10 to the minus 7 radian. So the distance from the Earth to the Sun is known, and we know this. So we know the distance on this side and this side. So you can use just your knowledge of sine, trigonometry. Opposite over hypotenuse is sine. So sine of alpha is opposite, which is this value, divided by the distance to the star, which is 10 to the 17, 4.6 times 10 to the 17. You then do the inverse of sine, and you'll get the angle that it gives you, 3.26 on 10 to the minus 7. Well, you'll see that is larger by 50% roughly than the value that they said it must be larger than. So therefore you say this is greater than that. Therefore the distance to this star can be determined using the parallax method. Okay, so what do you get marks for in this question? For question 19, use trigonometry to calculate the parallax angle. So we've done that. There's our trigonometry. Smallest angle, they put this as approximately 3.3 times 10 to the minus 7 radians, because here they've only got 2 significant figures, so this should be 3.3 ideally, yeah, to 2 significant figures. You then have to compare the calculated value with the 2, okay? So I'm seeing where you get the other mark from. Smallest angle. Okay. So that's what they've put as the solution. I'll let you stop and see because it's a... Yeah. So you worked out the parallax angle, used trigonometry. I think that's all it is. So it's pretty easy mathematically. Anyway, Cepheids, it then says part B. Cepheids are types of are special types of stars, which are known as standard candles. That means, yeah, that wherever you see a Cepheid, you will be able to use it as what they call a standard candle. Okay. So describe how these things called standard candles can be used to determine distances to stars. So if the distance is greater than the parallax method, you can use the standard candle method. Okay, describe how. That's your job, is to describe how you can use standard candles. Well, the luminosity of standard candles are known. So we know their luminosity, which is exactly how much power they're emitting at source. So if the intensity of these variable stars are measured at a certain distance, yeah, so they're at a distance, yeah, the inverse square law, so whatever that you're measuring them, so, and you know, for example, you have one in that you've measured the distance to, for example, by the parallax method. So like we did here, that this alpha was less than the was greater than the minimum angle required. So we know already a value for one of them. The inverse square law can be used to determine the distance because we know luminosity, we've measured the intensity, and therefore we can work out the only unknown, which is the distance. And that's how you get the 3 marks. Okay, so that's how you use the standard candle method. You compare 2 Cepheid variables at different distances, and you can then work it out. Part C. Just making sure I'm going on the right page. Part C is about the Sun. The Sun is a yellow star with a surface temperature about 6,000 Kelvin. In the 20th century, astronomers discovered a large variety of stars in our galaxy. Hertzsprung and Russell developed the Hertzsprung-Russell diagram, which is this. This is the Hertzsprung-Russell diagram, as a way of classifying stars. The HR diagram, as they're called, Hertzsprung-Russell, is shown below. So on the left hand, on the y-axis, we have the luminosity compared to the Sun. So the Sun is in this zone, okay? And this is the main sequence stars. That means the ones that are in the main part of their life, which is fusing hydrogen, okay? So over here, our Sun will be here. So we know that the 6,000 Kelvin will be here. They want you to label the x-axis to see that you know what the x-axis is. If this is the luminosity compared to the luminosity of the Sun, they want you to then tell us that the temperature is the horizontal axis. The other thing they want you to know is that they want you to remember that this is not a linear scale, and as you go this way, the temperature decreases. Yeah? So temperature decreases. Normally we would go this way and the temperature increases. So you see from here to here, it's doubled. And then the next time it doubles again, and that's what happens with log graphs. It's not a linear scale. Okay? So they want you to label the axis. So we've done that. And you should use approximate values, which we did. So we put 3,000, 6,000, and 12,000. If you put 3,000, 6,000, and 9,000, you wouldn't get the second mark because you've got to show that the temperature is doubling every so often. Okay? And then it gives us some information about the zones. So you see the zone 1, zone 2, zone 3, zone 4, and zone 5. So there are 5 zones identified on the HR diagram. Complete the following table. You should match one zone with each description. High mass hot stars. High mass hot stars. Well, hot is this way. So the hottest are this one. So I would put Z1. Okay. High mass, and how do I know that it's hot? Why don't I put Z2? Well, although it's hot, yes, it's not the highest mass. These are not as hot because the luminosity is not as bright. So these are actually if you like, these are stars that are dying, they're cooling down, okay? So it could be a white dwarf, for example, here. So basically, this is a hotter star that's fusing because it's a much larger, more massive star. So these are more massive. And as you go down this way, this is called the main sequence, yeah? the main sequence of the HR diagram. As you can see, as they go cooler, it means they're less massive. Okay, as you go this way, they're more massive and therefore hotter. All right, so high mass, low mass cool stars, Z5, I've put. Low mass, as we said, this is lower mass, cool stars. These are the coolest, so I put Z5. These are the hottest. And then low mass hot stars. Low mass hot stars, Z2. Low mass, yeah, and hot, because they're still quite warm, but they are still cooling down. So as they cool down, they'll move back this way, okay? All right, so that's how you do that question. And we're on question 19, is that right? No, we've done 19. We're on the last part of question 19, yes. The last part of question 19 is an asterisk. It means it's a 6 marker, okay? And it's the quality of your written communication that will get you the marks. The position of a star on the HR diagram changes as the star evolves. So remember I said the main sequence is the band in the middle. Over here are giants. Yeah, what are they called? Red giants. And then some of them will be supergiants. Over here will be white dwarfs. Okay? So the main sequence, red giants and supergiants, will be this way, for example. These ones with a larger mass and hotter will be things. So we want to talk about the evolution. So our sun will go from being in zone 3. When it runs out of hydrogen, it will try to burn helium, becomes a red giant, it expands. And then when it runs out of helium, it will basically give you a little explosion. It will shoot out the exterior gases, and then the inside will become a small dense object which will gradually radiate its heat, and over time it will cool down or become a white dwarf. Okay, so that's the essence of what they want you to talk about. So here I've written in Z3, a star like the sun in this zone is fusing hydrogen into helium in its core. Okay, this is, you could add, this is a main sequence star. Okay, so main sequence means burning hydrogen, fusing hydrogen. When it runs out of hydrogen to fuse, the core of the star cools. Okay, the pressure drops and it collapses under the force of gravity. The pressure drops. Okay, so what happens under the force of gravity? That's the second mark. So one for that, one for that. It then expands into a red giant. So as long as you know that it expands, you get another mark into a red giant star, and you've got to mention the zone, Z4. So make sure you know where it is on the Hertzsprung-Russell diagram. So it's not so much, this is the way the examiner wants you to write it. I think this is a lot of describing in here. If the temperature of the core is high enough, helium fusion can begin. Okay, so in zone 4. So once it expands, the temperature of the star, if it's hot enough, will cause fusion to occur again, but this time with helium. Okay, when helium begins to run out, fusion ceases again. And a star like, so again, fusion will cease. So after zone 4, a star like our sun it implodes, low pressure in the core, due to low pressure in the core, and it ejects its outer layer and becomes a white dwarf. The core becomes a white dwarf in zone, which is in zone Z2. So now this is how clearly you explain it. Now if I show you how they're looking to mark this, 4 of these points, if you make 4 of these points, you'll get 4 marks, okay? As long as they've understood your English. Okay, then to get the extra 6 marks is how you make the connections between the 4 points. So it's the quality of your written communication. Yeah, so if your answer shows a coherent and logical structure with linkages between the points you've made, you get an extra 2 points. So 4 points for getting the points that are listed on my answer, which I've taken from here. This is what they're looking for in terms of the content of your answer. And this will be the quality of your written answer. So I've used their mark scheme to try and explain what they're trying to say. Okay, so you can pause the video, have a look at the mark scheme and see what you think you deserve. Okay. The next question. So that's 18 markers. So the big question, biggest question so far. The last question is question 20. So this isotope, actinium-225, it decays to francium, okay, which is a group 1 metal, by emitting alpha particles. Actually, each isotope, each individual nucleus will only emit a single alpha particle, which is what this equation is showing you. So we're only looking at one particular case. So it has a short half-life, okay, which makes it suitable for medical applications, because you don't want medical applications, something with large half-lives, because they usually inject them into your body. Okay, so the medical applications are often called medical tracers. Okay, so you have the numbers, they've given you the numbers of actinium, and you've got to work out, knowing there's alpha, what the other numbers are. So if you get the top numbers adding up to 225 correctly, 4 and 221, you get 1 mark. And if you have the bottom numbers, the proton numbers, 2 protons in an alpha particle, 87 are left for the nucleus that remains. Okay, so 1 for the top line and 1 for the bottom line. The bottom line is charged particles, top line are nucleon numbers. So in a radioactive decay, energy is released and the total mass decreases. Well, the energy released is because you're producing something more efficient, yes? So the mass on this side is less than the total mass here. So you've released some mass, and if you do that, that goes into energy using E equals mc squared. Okay? Show that the energy released, if the mass decreases by 1 atomic mass unit, is about 930 megaelectron volts. So they want you to show that 1 unit is approximately 930 megaelectron volts. Well, this equation, the E, gives you a value of joules if you know the mass in kilograms. Well, 1 unit on your data sheet is 1.66 times 10 to the minus 27 kilograms by definition. So if you now use this equation, and if the mass decreases by a complete unit, that will be 1.66 times 10 to the minus 27 multiplied by the speed of light squared, and it gives you this value. That's how much you would get in joules. Well, we want to see, well, what is this in electron volts? So to convert from joules to electron volts, you always divide by the charge of an electron, okay, or the size of the charge of an electron. So because it comes from E equals QV, where joules and volts and charge are linked, okay? So we want to know what voltage equivalent that would be. So the energy in electron volts is the energy in joules divided by 1.6 times 10 to the minus 19. So you divide this number by this number, and you'll get how many electron volts that will be. So it comes out to 9.34 times 10 to the 8, which is approximately 930 megaelectron volts to 2 significant figures. So you've answered the question. Okay, hope that makes sense. Part C. The francium nucleus and the alpha particles move away from each other. Why? Well, this is 89 positive protons, yeah, and this is 2 positive protons, okay? So when they are ejected, they're basically, it's like an explosion. This one will recoil, and this one will go forwards, okay? The one with the smaller mass will get more velocity, yeah? The one with the bigger mass will get smaller velocity. Okay, explain why the kinetic energy given to the alpha particles is just less than this, 5.9 electron volts. Okay, now the mass decrease for the decay wasn't 1 unit. That was just something that we were doing to prove that 1 unit is approximately 930 megaelectron volts. Okay, so remember, 1 unit is what we calculated was 934 megaelectron volts. Yeah. So they're saying the kinetic energy given to the alpha particle is less than 5.9. Well, first of all, how much is this? This is a fraction of 1 unit. So if we multiply this, a fraction, so rather than 1, this fraction of 1 will be the equivalent fraction of in megaelectron volts. So energy released is still using E equals mc squared, which is a fraction of 1 unit, yeah? This energy released, yeah, is a fraction of that. So all you've got to do is to multiply this value by 934 if you want to use the accurate value, or you could use it with the accepted value, which is 930, which I think is on the data sheet. You'll either get 5.93 or 5.91, but this is slightly more than 5.9 megaelectron volts. Okay, so why does the kinetic energy given to the alpha particle is less than 5.9 megaelectron volts. Well, this energy, this energy in the explosion causes, it's like an explosion, isn't it? Causes the francium nucleus and the alpha particle to move in opposite directions due to the conservation of momentum, which I explained before. As the francium nucleus is much greater than 50 times, 89, 91, it's 45 times. It's greater than 50 times. It's about 45 times, it's actually 44 times the mass of the alpha particle. Oh no, it's not, because we're talking about 225, so it's greater than 50 times. I was right in the first place, because remember, the mass is not just the protons. The recoil velocity is much smaller than the alpha particle, so most of the alpha particle gets most of the velocity. And remember, the kinetic energy is equal to half mv squared, then the velocity is the main factor to determine the kinetic energy. So therefore, the alpha particle gets most of the available 5.9 megaelectron volts. So there's, if we count this as roughly 5.9 megaelectron volts, it won't get all of the 5.9 megaelectron volts, because some of the velocity and kinetic energy available goes into the recoil of the francium nucleus. Okay, so it can't get all of it, so it'll be slightly less than that. So whether you want to add a little bit more in there, it's up to you, the clarity of your answer. So we're talking about 20 part A. I'll let you have a look at that while I get ready for the next part. Okay, so that's the mark scheme that you can look at later on. We're now on part, we're on part D, the final part. So the activity, this time it's about activity of a sample of actinium is 7.4 times 10 to the 7 becquerel. So that's the initial activity when it's prepared. So when it's prepared, it's time 0, so activity 0. Calculate the number of actinium atoms in the sample 7 days later. Okay, the half-life is 9.9 days. So it's, you have to use the equation to be able to work it out. Okay, because obviously it's not a simple fraction like in GCSE. 7 days later, the half-life, so it's less, it'll be less than, so 7.4 is less than the half-life. So it'll be less than half, it'll be more than half of 7.4, the answer. Okay, so let's see. So we first need to work out the decay constant, because you've got to use natural logarithms to work it out. So the natural log of 2, this equation is given to you in your equation sheet. So once you know the half-life, of course you want the half-life not in days, you want it in seconds. So you multiply by 24 to get in hours, 3,600 to get in seconds. So you do this divided by the half-life and you'll get the decay constant. Okay, so that's lambda for actinium. Then we know that activity, also on your equation sheet, is equal to the decay constant times the number of atoms that are about. So the activity is decreasing as the number of atoms decreases, which is why there's a minus sign. Okay, it's a decrease. So you can see that both these equations are on the data sheet. So then we know that N0, when we're talking about the original activity, N0 will be the original number of atoms, will be equal to the activity at time 0 divided by lambda. Okay, so we know that we can work out what our original number of atoms giving this activity would be, because we know A0 and we know now the lambda, so we can work out the original number of atoms that gave rise to that activity. So we know the original number, N0, is 9.1 times 10 to the 3 at times t equals 0. We then know another equation from your data sheet, that 7 days later, we want to work out what it will be. So n after 7 days. Yes, so t would be 7 days in here. Again, we need it in seconds. So we know n equals n0. Well, we know n0 is that, so we know the value there. We know e. We know lambda. The only thing we don't know is t. Okay? Oh no, we know t. We know t. The only thing we don't know is n. So we know this, we know this, we know this, and we know that. Okay? So all you've got to do is put your numbers in. So there's n0. There's e to the minus lambda times t, multiply by 24 to get in hours, multiply by 3,600 to get into seconds. Okay? You put the numbers in your calculator, and you can just use the e value. Once you know how to use that, you put the numbers in and you'll get this number out, which, as I said, is more than half of the original number. Yes, because they're both to the same Oh no, I'm talking about more than half of this original number. Yeah? So it's about 5.6 to 9.1. As it is, that's more than half, because 7 days is not quite equal to the half-life. If it was 9.9 days, it will be exactly the half of that. Okay? And if you do round it up, it will be to two significant figures that. Okay? So you'll probably get a mark for this, a mark for this, and a mark for this part of the question for your final answer. Well, that ends the 1 hour and 45-minute exam, which is what the length of the exams are in year 13. The year 12 ones are 1 hour and 30. Yeah? So you see that exam, Unit 5 is 1 hour and 45 minutes. And that finishes our coverage of January 2022. So if you liked the video, please give us a thumbs up and share it with your friends. So we do really want to get more people viewing it. The channel is growing, but obviously we need to your help to make sure we will continue to make these videos. So please like and share, and also subscribe if you want to know when I do the next video. So probably in the next few weeks we'll be going through the 23 and eventually the January 24 paper as well, which I'm going to use as practice exams for my students under exam conditions. Okay, well, hopefully see you in the next video. Bye for now.